Hi everybody, this is Mrs. Dinkelman, and these are the notes for lesson 4.1, which is titled Approximating with the Tangent Line, and then also Applications of Rate of Change. So sometimes you'll see this approximating with the tangent line called local linearization or just linearization, and many books tend to have a specific formula for it that looks a little bit different, but it's really just writing the equation of the tangent line and using that to approximate what you're doing. So if you look at example 1a here, since the x-coordinate really wants us to approximate as 2.1, you'll see that we're going to use the tangent line when x is 2. In fact, 2 comma negative 2 is what they gave us because we have an implicit. But since 2.1 is close to 2, we should be able to find the tangent line at 2 and then just replace our x-coordinate in that equation with 2.1. So we'll see that here. So let's go ahead and find the derivative of this particular example. So like I said earlier, it looks like an implicit problem because we have a mixture of x's and y's. So that's my indicator there. So remember, I will do 2x dx and then 2y dy and then 2 dy equals 0. I'm going to go ahead and do two things at once. I'm going to leave the dy stuff here on the left-hand side and factor out the dy, and then move that thing with the dx over to the left-hand side. Remember, the next step is to really divide by dx. And then I'm also going to divide by both sides by this 2y plus 2. Okay, so for dy dx, I have negative 2x over 2y plus 2. Now we're welcome to simplify that. I'm not so worried about the 2's. I don't think that's going to make our life too difficult. So we're going to plug in 2 and negative 2, so 2 for x and negative 2 for y. So negative 4 divided by negative 2, which is positive 2. So there's our slope. So we're going to say our tangent line is slope x minus the x-coordinate plus the y-coordinate. And now what they're intending us to do is to plug in a 2.1 right there. So we're saying that something like, we're just going to go approximate, I guess. I wish this was in function notation, but it's not. So I kind of don't know what to write there. Okay, so we're going to have, again, we're plugging in the 2.1 there, so we're going to 0.1 in there. So 0.2 plus negative 2 is negative 1.8. So that's what we're saying. We think that the point is something like 2.1 comma negative 1.8. Now, of course, that's an approximate because we're using this tangent line here. And for 1.9 then, we're going to do the same thing. So we'll plug in a 1.9 for x. So in here, we're going to get 2 times negative 0.1. So we're going to get negative 2.2 for that one. So that's our approximate for that. Sometimes they give us the information like on example 2 here. So remember that this is the slope, and they're saying our point is 2 comma 3. So we're just going to write the equation of the tangent line. So slope x minus the x-coordinate plus the y-coordinate. And now we're going to approximate. So I like that they have function notation here. So I'm going to say f of 2.01 is approximately, and I'm going to go ahead and plug that in for my x value into my tangent line. So let's see, that's going to be negative 2 times 0.01. Okay, so 3 minus 0.02. So 2.98 is our approximate. So that's that first part, is just using tangent lines to approximate in case it's difficult for us to figure out what 2.1 is. Like on example 1 here, I don't really want to plug a 2.1 and try to figure out what the y-coordinate is. So that tangent line was very much easier. Okay, and then sometimes we have to interpret these rates or interpret graphs in terms of some sort of context. So over here we have this rainfall in inches per hour. Let's see, from midnight to 6 a.m. So there's a couple things we want to do on these. We want to make sure we include units. We want to talk about that it's at a specific time. We want to make sure we include all the details in our sentences. So it's talking about on number 3, point A, and if we look, that's just a y-coordinate, and the y-coordinate is 1 inch per hour because this is modeling the rate. So we might just start with saying, okay, we know it's a 1 inch per hour, and then we have to write a sentence. So something about the rate at which rain is falling. to hear the bell in there. Let's see, that's going to be at what time? 3 hours after midnight. So at 3 a.m. is 1 inch per hour. Okay, what's the slope between A and B? Well, the slope is 0. And what does that mean? It means our rate is not changing or our rate is constant. So on 5, when we write our complete sentence about our answer to 4, so let's see, A to B is like 3 a.m. to 4 a.m. So from 3 a.m. to 4 a.m., the rate at which rain is falling is constant, or is not changing would be fine. Okay, between B and C, now we have to be careful because of the units and scale that Gary put on here. So if we go down, we're actually going down 1 inch and then over 1 hour. So it's down 1 over 1. So the slope between B and C is really -1. And so what that actually means is the rate is negative. So our rate is decreasing, it's getting slower. There's lots of ways we could describe that. And this is between 4 and 5 a.m. So let's see if we can say from 4 a.m. to 5 a.m. the rate of rainfall is decreasing. That's rainfall is decreasing. So it's slowing down a little bit. Have to be careful about slowing down. We'll talk about that at some point. Maybe we already have. Is decreasing at, and so this is -1. So the rate is in inches per hour. And then again, look over here. Our y is in inches per hour. And if we're talking about slope, we're talking about a y over an x. So this is going to be in inches per hour. And we can actually just do it like that, inches per hour. Or we can call it inches per hour squared. So however you want to name that, they'll be happy.